For the past couple of lessons, we've been talking about this thing called the flat memory model. What the heck does that mean? Well, in a nutshell, what it means is that the addresses from the point of view from the software relative to the hardware is we just start with address 0 and count up to as high as we can count. Remember, we were way back talking about how high can we count with 10 fingers, right? Well, we talked about, well, what if we use them as switches, as binary? So you had 0, then you had 1, 2, 3, and so on, right? And once I get to this number, I've used up all the possible numbers I can represent with 10 bits, right? 10 bits. And that in a sense is really what a flat memory model is. I am just simply counting up from 0 all the way up. Now, that is kind of differentiated from something called a segmented memory model. We'll also talk about paging. And those, what they do is they take that model and they move it around. They make it so that it's easier to access by using 2 steps to reference an address. But we're just going to use the 1 step. Just, I have a certain number of bits and my addresses go from all 0s to all 1s. In fact, let's go ahead and do an example. Let's say that my processor has 20 bits for the address. 20 address bits. Now, what does that mean? Well, that means I can count from 0 all the way up to 21s. And what is 21s in hexadecimal? Well, it's 5 Fs, right? It's 5 nibbles of Fs. Now, the way we represent this whenever we're talking about, designing or explaining how the hardware works, how the hardware is designed, is we have this thing called a memory map. Now, a memory map is actually just a rectangle. Very long, tall, skinny rectangle, okay? Now, this long, tall, skinny rectangle represents starting, and I've seen it go one way or the other, but I typically start with the all 0s at the bottom, and so we'll just say that that's a hexadecimal all 0s. So, and there's 5 nibbles there to correspond to our 20-bit address, and we count all the way up to our 5 nibbles of Fs. All right? And so this is our memory model. This is the way we're representing how our particular processor is going to represent different components of memory. Now, the reason why it's really important to use a memory model to describe the system is that, remember, there's more than one memory device we're going to be communicating with. There's multiple memory devices we're going to be communicating with. And they are located based on their chip selects, which we talked about in the previous lesson. They're located in different ranges. I mean, for example, we'll talk about a BIOS. And a BIOS is that basic input-output system. It's the code that is hardwired to a degree. I mean, usually it's in some sort of a flash memory. It's hardwired so that whenever the machine is shut down, it's off. When it comes up, there's nothing in memory. Memory is volatile. Everything that was in memory is gone. So the processor needs something to execute so that it can start populating memory, so that it can start accessing things like its external storage devices, the hard drive, or a network boot, or something like that. And so the BIOS is a really important thing. Why don't we put a specific range for a BIOS? Now, it's not going to be very big. We'll just put a little BIOS down here. And we'll have it say, okay, the starting address is going to be 04000, and it's going to go up to 05FFF. So it's not very big. It's not very big. We'll just put this little guy here. All right, now, we do need memory too. We need some sort of a RAM, so some main memory. So why don't we put a main memory, and this, by the way, is not going to be drawn to scale, but I'll do my best. So we have main memory here. And let's say that the size of the memory and basically what the BIOS is going to be looking for in order to populate memory, let's just say that it goes from a hexadecimal 40000 up to a hexadecimal 7FFFF. All right, so there's our main memory. Now, I also talked last time that it's not always just memory devices that are being communicated to through these addresses. Sometimes there's hardware devices. For example, we might have some sort of a graphics card. And that graphics card needs to have interaction through a memory. I mean, it's actually going to pretend to be a memory. You know, whenever you want to store a bunch of data to a memory device, to a graphics card, you know, what needs to be displayed on the output, the processor is storing data to what looks like a range of addresses, but they're special purpose. That's what the GPU is using in order to display something. And we're going to put this at the very top of our memory model, and it's going to go from E0000 up to FFFFF. All right. Now, the other portions, well, we may have other devices, other things that are in those portions, but for now, let's just go ahead and leave them empty. We'll worry about these three guys for now. Okay? Now, we need to figure out how the hardware, and we talked in the last episode about the chip select. We need to figure out how the hardware of the chip select is going to be set up in order to activate the BIOS just in that range, activate the main memory in just that range, and activate the graphics card in just that range. So think about it this way. There are going to be three separate chip selects, one for the BIOS, one for the main memory, and one for the graphics. Okay. All right, there's three of them. Now, I could say write an address, and I'll just pick an address. How about 0x05132? All right, so there's a hexadecimal address. Which one of these guys did it land in? Well, it landed in this range, right? Which means the main memory and the graphics card need to be off. Their chip selects are going to be ones. What is the chip select for the BIOS? It's going to be a 0 in order to turn the BIOS on. Let's say that I picked an address and I'm writing to an address, I don't know, how about 89DC2? All right. Now, 89DC2, that's right there. It's not on any of these three devices. And so all three of these chip selects are going to be off. Okay, let's say that I'm going to E295B. All right, that is up in this range, which means the graphics card will be enabled, but the chip selects for the other two will be off. Let's give main memory a chance here, hey? So how about we're going to write to, I don't know, how about 69D2C, all right? And that is going to be somewhere in there, so that means the main memory chip select is going to be on, but the other two are going to be off. All right. So what does the hardware look like when we're trying to design this system? Let's make some room here. All right. Now, to do this, we are going to do kind of backwards from what we did the last lesson. We are going to determine the low and the high addresses for each one of these devices in binary. We got to do it in binary so that we can figure out which bits are going to be assigned to the chip select, which bits are going to be assigned to the address lines going into the device. From this, we can also figure out the size of the memory device. And in fact, I didn't do this, but let's go ahead and do it now. What is the size of the processor's memory space? How big a memory space can the processor see? Well, it's the number of patterns of ones and zeros for 20 bits. So that's 2 to the 20th, which is equal to 1 meg. All right. And by the way, as a quick aside, you've got 2 to the 20th. Well, let's do it up here. 2 to the 10th is equal to 1K. 2 to the 20th is equal to 1 meg. And 2 to the 30th is equal to 1 gig. And, well, it goes up from there. But that's about all I've got room for right now. All right. So let's start out with the BIOS. The BIOS, the low address is 0, and I'm going to convert this to binary, so it'll be 0. And then we've got 4, 0, 1, 0, 0. And then I've got 3 nibbles of zeros. 1, 2, 3. All right. Now the high address, it's going to be 0, then 5, and then 3 nibbles of Fs. All right. Now, there's really something important you have to notice right up front in order for this to make sense. The only way this makes sense is if you can put a line that separates the bits that stay the same. Notice that all the bits on the left side here, they stay the same. All zeros up to then a 1, 0. So you have 5 zeros, 1, 0, 5 zeros, 1, 0. Those are all the same. This defines the chip select. All right. Now, look at the other side of this line. The other side of this line, all the bits go from all zeros to all ones. And remember, when we were talking about the memory device's perspective on the address lines, as far as the memory device is concerned, its lowest address is all zeros. Its highest address is all ones. So notice when I picked those numbers, I actually was picking them on purpose to be a certain configuration so I could draw that line so everything to the left stayed the same in order to define the chip select. Everything to the right, well, these guys are address lines to, and in this case, the BIOS. But they're the address lines that are going to the memory device. So we can right up front tell one really important characteristic. How big is the BIOS? Turns out the BIOS is as big in terms of memory addresses as the number of address lines that are going to its address line inputs, okay? How many is it? Well, this is A0, A1, I'm not going to cram all those in there, A2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we go all the way up to A12. So A0 to A12, that's 13 address lines. All right. How many patterns of ones and zeros can 13 address lines take on? 2 to the 13th. 2 to the 13th is the same thing as 2 to the 3 plus 10, right? Which is the same thing as 2 to the 3 times 2 to the 10. Well, we know that 2 to the 3 is 8, and we know that 2 to the 10 is 1K. So this BIOS, and yes, I know that that's not very big. That doesn't sound very big. It's not very big because I'm using a real small address space so that I can fit it on the board. But that said, I've got 8K. That's my size of my BIOS. All right? So I know how big the BIOS is. What does the chip select look like, though? Well, the chip select is set up so that it turns to a 0. Remember my truth table from before. It turns to a 0 whenever this pattern of ones and zeros is on the address lines. Anything that's below this pattern of ones and zeros will change, but anything that's below this, that's going to change. Anything that's above it, that's going to change. So, as long as we're looking at that pattern of ones and zeros, it's going to turn the BIOS on. So let's do this. This guy right here is a 13. This guy is a 14, a 15, a 16, a 17. There's a lot of these. A 18, a 19. And you got to take into account all of the address lines coming from the processor, A0 to A19, all 20 of them. Because if you leave some of these off, remember, that BIOS is going to find itself duplicated in this memory map, all right? So, how do you make an active low chip select? Well, first of all, it's done with the decoder circuit, but the active low means that it's going to be a NAND gate, all right? Think of it this way. The decoder starts with a D-shaped gate. That's an AND gate. Make it active low by putting the inverter on the output. So we've got A19, A18, A17, A16, A15, A14, and A13. All right, so there's all of our address lines. Now, A14 is the only one that needs to be a 1. Everything else gets inverted before going into this NAND gate. So we've got inverters for every single one of these guys so that the only thing that is going to turn this chip select, activate this chip select, is a 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, On those address lines, it'll turn on the chip select for this BIOS. All right? All right, now remember, this has got, because of the size of the BIOS, it being only 8K, there are a lot of address lines left over that we had to use to define this chip select, seven of them specifically. When we take a look at main memory or the graphics card, we'll see that it doesn't necessarily, those guys are going to have a different number of bits left over in order to place those. So let's get the main memory next. Okay, now for the main memory. And once again, we'll start out the same way we started out before. We're going to do the low and the high addresses in binary so we can figure out where the patterns of ones and zeros, where we can divide those two from the chip select bits and the address lines going to the memory device. So we're going to start with the low, and that's 4. And then there's 4 nibbles of zeros. So 1, 2, 3, 4. All right. Now, let's look at the high address. The high address is 7. All right. F, 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 F. All right. Now, our line is drawn a little bit further to the left this time, isn't it? In fact, way farther to the left. We come up here, and that is where that line occurs. Wow, so what's the size of our memory? Well, we've got 4, 8, 12, 16, 17, 18 bits. So that's 2 to the 18th, which is equal to 2 to the 8th plus 10, which is equal to 2 to the 8th times 2 to the 10, which is 256K. All right. Now, once again, we are working with some small addresses here, just so I can fit them on the board. But what does this mean whenever it comes to our size of our memory and how it fits in the memory space? Well, I've only got a 1 meg memory space. If you divide 256K into 1 meg, how many times does it go? 4 times. 4 times, which means it turns out that there are, because these bits are used by the 18 address lines going to the main memory, there's only 2 bits left over. Those 2 bits left over mean there's only 4 possible places I could have put this 256 meg memory. I could have put it at 0, 0, which would have been in the bottom quarter. I could have put it 0, 1, which is where I put it in the second quarter. I could put it at 1, 0, that would be at this quarter, or I could put it at 1, 1, which would have put it at the top quarter of the memory space. So that turns out there were only 4 places I could have put this memory. Now the key is that this memory can't overlap with any of the other memories. So you have to rearrange things around so that main memory is going where it should go. And in fact, the same thing could have been said for the BIOS. But since there were less address lines going to the BIOS, there were, 7 bits we said? So 2 to the 7th is 128. So there were 128 places I could have put the BIOS. But you can't have them overlapping, because if you have them overlapping, 2 chip selects are going to be low at the same time, and you'll get bus contention. There'll be 2 devices that are trying to talk to the bus at the same time. The output will be garbled. All right? So let's go ahead and figure out what our chip select looks like. So this guy right here, remember that's A0. So we've got A0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This guy right here is A18. This guy right here is A19. So what we need to do is turn on main memory when A19 is a 0 and A18 is a 1. It's a simple NAND gate. So this is the chip select for the main memory. It has A19 is a 0, A18 is a 1. That was pretty simple, right? And if I had no inverter here, if this was just A19 and A18 both going directly in there, so it is a 1 and a 1, that would have made it so a 1, 1 was here, and the main memory would have been moved to the top quarter of our memory map. So let's do the last one. The graphics card. How are we going to get the chip select for the graphics card placed in our memory map successfully with a chip select? Now we're going to do things exactly the same way we've been doing them. For the graphics card, we've got the low address of E, which is in binary 1110, and then 4 nibbles of zeros. All right. Now, the high address. That is all ones. It is at the top, right? So these are all binary values, right? Now, can you draw the line? Can you draw the line that separates the address lines that are going to the graphics card from the address lines going to the chip select? Well, if we put it right here, you see that we have all zeros to all ones. Those are the address lines going to the memory device. The graphics card memory device, right? And how many of them are there? Well, there's what? There's 16, 17 bits, so 2 to the 17th means that the size of our graphics card memory space is 2 to the 7th times 2 to the 10th, which is equal to 128K, all right? Now, what does our chip select look like? Well, remember, these are the address lines defining the chip select. These are the address lines to the memory device. And the memory device is, as always, going to look at addresses going from all zeros to all ones. So what does the chip select look like? Well, remember, this is A sub 0 all the way up to A sub 16. So this guy is a 17, a 18, and a 19. So our chip select, which once again is going to just be a NAND gate, is going to take as its inputs a 19, a 18, and a 17. Do I need to invert any of them? No, because it's just an AND, right? The AND. I want to output an active signal when A19 is a 1, and A18 is a 1, and A17 is a 1. They all go straight in. All right, and that gives us our chip select for our graphics card. And there you go. 3 chip selects, 3 kind of different chip selects, right? One very, very small, one about 1/4 of the size, and one about 1/8 of the size. How did I know it was 1/8 of the size? And it's not about, it's exactly. So we have a very small one, we have one that's exactly 1/4, and one that's exactly 1/8. How did I know that it was 1/8? Well, because the number of address lines going to the graphics card makes it so that we cannot have any more or any less than 3 address lines left over for the chip select. How many patterns of 1s and 0s could I have for 3 bits? 8. So I could have had 0, 0, 0, which would have put it in the bottom quarter, or 0, 0, 1, and so forth, all the way up to the top. Now, bottom 1/8. The key is they just can't overlap. There you go. 3 chip selects.